February, March 2023, paper 6, variant 2. Question 1. The student determines the diameter of a marble by two methods and calculates the density of the material from which the marble is made. On figure 1.1, measure the length D. Can I measure the length D using my ruler? Yes, the length would be around 7.8 centimeters. Again, if your reading is slightly less than 7.8, it's okay due to the printing error. Sometimes when you print, the distances are a bit smaller. Using your value of D, calculate the average diameter D1 of one marble. So if I want one marble, how many marbles do we have? We have 5 marbles. So 7.8 divided by 5. What's 7.8 divided by 5? This will give you a length of 1.6 centimeters. 7.8 divided by 5. Suggest why is it more accurate when using a ruler to measure the distance D of 5 marbles rather than measure the diameter of one single marble. One single marble, there would be an error, right? There would be an error, a human error. So basically, we want to decrease this error. We want to decrease this percentage, okay, of uncertainty. Sometimes we call it uncertain. I'm a bit uncertain whether I started at zero or not, or if there is a zero error on my ruler. Sometimes, so to decrease, okay, decrease the percentage of error. Okay. Hmm. Figure 1.2 shows two wooden blocks and one of these marbles. Describe how the student can use the two blocks to determine a new accurate value for the diameter of the marble. How can I find a more accurate value for the marble instead of using 5 marbles? What can I do using these two wooden blocks? Okay, to draw the diagram, basically we want to draw the wooden blocks and place the marble between them, right? You need to place the marble between them. Why? Because you actually need to measure the distance between these two wooden blocks. So using a ruler, okay, using a ruler, you will measure the distance between these two wooden blocks. Okay, so place the marble, place the marble between the two blocks and measure, okay, measure the distance between them. Between them using a ruler. Student uses top pan balance as shown to measure the mass of the 5 marbles. Initially, the reading was 30.8 grams, and finally, the reading was 64.3 grams. Can I find the mass of one marble, the average mass of one marble? So first of all, can I find the difference to find the mass of the 5 marbles? Yes, the difference would be 64.3 minus 30.8. And then if I want only one marble, this would give you 64.3 minus 30.8 would give you the mass of 5 marbles. Can I calculate it? Yes, 64.3 minus 30.8. This is 33.5. So this is 33.5 grams. The mass of 5 marbles together. To find only one marble, you can divide by 5. Okay. To find only one marble, we can divide by 5, which would give you a reading of 6.7 grams. This is the mass, or the average mass of one marble. Student pours water into a measuring cylinder. Volume of the water was 26 centimeters cubed. When he added 5 marbles to the measuring cylinder, can I take the new reading? Yes, I can take the new reading. Is it 40? Is the new reading 40? No, it's not 40. Take the reading from the bottom of the meniscus, which is 38 centimeters cubed. Okay, you have to take the reading from the bottom of the meniscus. Now, can I find the volume of one marble, the average volume of one marble? Yes, V2 minus V1, 38 minus 26 divided by 5. 38 minus 26 divided by 5 is 2.4. Okay, average volume of one marble. Can I find the density now? Yes, density, mass over volume, 2.4. This is the volume, and the mass is 6.7. 6.7 divided by 2.4. Divided by 2.4, which is 2.8 grams per centimeter cubed. Describe one possible source of inaccuracy in this method. Okay, described in C, and suggest one improvement to reduce its effect. So in C, what did he do in C? He measured the mass using the measuring cylinder, using the balance, and then he found the volume using the measuring cylinder. Uh, um, hmm. So one possible source of inaccuracy could be what? For example, the measuring cylinder is too large. The graduations on the measuring cylinder is too large. Or for example, okay, when you put the water in the measuring cylinder, you didn't take the reading perpendicular. It could be, or you didn't take the reading from the bottom of the meniscus, for example, right? So if we say that the graduations on this measuring cylinder are too large, they are 1 centimeter cubed apart. Is that too large? It could be too large if we are talking about very small volumes. If we are talking about very small volumes, if I want a volume of 3, 4 centimeters cubed, yes, this could be a very large graduation. So possible sources of inaccuracy that the graduations mm, on the measuring cylinder, okay, are too large. How can I improve that? By getting a thinner measuring cylinder, okay, or a measuring cylinder with smaller graduations, okay, or mm, using a smaller measuring cylinder. Should my readings, okay, calculations, should they be 2 or 3 significant figures? It's up to you, okay? It's up to you. You can use 2 significant figures or you can use 3 significant figures. If you have a table, for example, okay, when we get to the table, for example, if all of the readings are two significant figures, then when you calculate or when you take a reading or whatever, then your reading has to be 2 significant figures. If they are 3 significant figures, then your reading has to be 3 significant figures. Okay. Now, in question 2, we have a thermometer. Can I take the reading of theta R, the room temperature? Yes, the room temperature would be 21 degrees Celsius. Describe one precaution to take the reading as accurate as possible. One very important precaution is to take the reading perpendicularly. Take the reading, okay, perpendicularly. Why? To avoid the parallax error. Okay, to avoid the parallax error. Experiment A, the student pours a volume of 100 centimeters cubed of hot water into the beaker and records the temperature theta A at time 0. She records the temperature every 30 seconds. Her readings are shown in 2.8 and 2.1. This is experiment A. Okay, the student repeats the process. She waits until the initial temperature of theta B of the water is the same value as the temperature of theta A at 90 seconds. Again, again, she repeats the process. She waits until the initial temperature of theta B is the same value as theta A at 90 seconds. What was theta A at 90 seconds? It was 85 degrees, right? It was 85 degrees Celsius. So in the first line of 2.1, should I write 85? Yes, you should write 85. Should I write it 85 just like that? No, point 0. Why point 0? Because all of the readings are three significant figures. Okay. Now, write a conclusion stating how the temperature at zero affects the rate of cooling of the water. Okay. Temperature at T0. Theta A started with 92 and ended with 80, so the temperature difference is 12 degrees Celsius, right? 85 minus 75, temperature difference is 10 degrees Celsius, which is slightly less. It does slightly affect the rate of cooling, yes. As the initial temperature decreases, what happens? Okay, as the initial temperature, as the initial temperature decreases, what happens to the rate of cooling? It decreases. Yes, I know it's not that huge of a difference, but again, it does decrease. It's not that huge of a difference because the starting temperatures, the initial temperatures, weren't that much different. 92 and 85, it wasn't that much of a difference. If the difference was, for example, instead of starting with 92, it started with 70 or 60 something, yes, you would have found a huge difference in the rate of cooling. So as the initial temperature decreases, okay, the rate of cooling also decreases. Hmm. Can I find x1, which is the rate of cooling? Okay, theta a at 90 degrees minus theta a at 180 degrees. Theta a 90, theta a 180. So 85 minus 80, right? 90 degrees and 180 degrees. 85 minus 80 divided by the temperature or the time taken, which was 90 seconds. So 5 over 90 is 0.0555 or 0.056 degrees Celsius per second. Degrees Celsius per second. Do not forget the unit, please. Can I do the same for B, but starting with B0 to B90? B0 to B90. What was B0 and what was B90? So B0 was 85 and B90 was 79.5, which is almost the same difference, right? 85 minus 79.5. This is a difference of 5.5 divided by 90. Okay, it's a very close value. What is this? 85 minus 79.5 divided by 90. 0.061. 0.061 degrees Celsius per second. So the student says that x1 and x2 should be the same. Should be the same. Are they the same or not? It's 0.56 and 0.61 to find the difference, to find the percentage difference. 0.061 divided by 0.056. Right. What is the percentage difference? 0.061, 0.056. 1.089. 1.09, right? 0.09. This is a 9% difference, which is acceptable. It could be considered, they could be considered to be equal. So are they the same? Yes, we do agree. Okay, yes, agree the same. They are, okay, the same. Why are they the same? Because 0.061 and 0.056, the values are close. Okay, they are close within the limits. Okay, within limits of experimental accuracy, you can say that the difference is less than 10%. Hmm. Say two variables which must be controlled. You have to have hmm, you have to have the same initial temperature, you have to have the same uh, volume of water, same room temperature, same room temperature, same volume of water. Why didn't I write same initial temperature in this question? Because x1 and x2 are already do have the same initial temperature. If you check out the numbers, x2 85 minus something, right? And when we found out x1, it was 85 minus something. So they already had the same initial temperature. We need to state two other variables which have to be constant, the same room temperature and same volume of the water. Someone also might say the same type of beaker, the same surface area of this beaker. On figure 3.1, draw a voltmeter to measure the potential difference across the length of the resistance wire. So in the voltmeter in parallel with this resistance wire. Can I take the readings of the voltage and the current and write them down in the table? Yes, the voltage is 1.3 and the current is 0.86. So voltage is 1.3, 0.86. Can I calculate the resistance? Yes, 1.3 divided by 0.86, which would be 1.5 ohms. Plot a graph. Draw the straight line of Westfit. Straight line of Westfit. R on the y-axis, R slash ohms, and then L on the x-axis, L slash centimeters on the x-axis. R 1.5 to 8.3. 1.5 to 8.3, so we can start with 1, 3, 5, 7, 9, 6, 8, 10. Or you can start with 0. It's might be acceptable. If you start with 0, 2, 4, 6, 8, 10. You have from 1.5 all the way to 8.3, so this is an okay scale. What about the length? 20, 40, 60, 80, 100. 20, 40, 60, 80, 100. Is it okay if I start with 0 for the length as well? Yes, you can start with 0 for the length as well. It would be acceptable. Now, let's plot the points, 20 and 1.5. 1.5, let me zoom in a bit. So this is 20 and 1.5. 40 and 3.6. 3.6. 6 and 4.2. 6 and 4.2. Okay. 80 and 6.6. 6.6. And then 108.3. 108.3. So it's obvious that 6.6 is a bit, it's quite an outlier. Let's draw the line of best fit and determine the gradient. Line of best fit would be, yes, this would be a really good line of best fit. You have 1 point above the line, 1 point below the line. It would be acceptable. Can I find the gradient? Yes, I can find the gradient. You have to draw the triangle method. Okay, you have to clearly draw the triangle on the graph. And then y2 minus y1, so 8.3 minus 1.5 over x2 minus x1, 100 minus 20. This is a gradient of what? Minus 1.5 over 80. 0.085. Okay, 0.085. Okay, the gradient is numerically equal to the resistance per unit length. Okay, write down a value for this experiment. So basically you have to write down the same number, 0.085. 0.85 ohms per centimeter. And that's it. It's just one practical reason why the students carrying out this experiment may not obtain the same readings. Why don't they have the same readings? We did the same things. We are trying as much as possible to be accurate. One of the very common mistakes is while using this crocodile clip. Okay, let's check out the diagram, the figure. You have this crocodile clip. One very common mistake is when you use this crocodile clip, you don't place it exactly at the indicated length. So sometimes the length is slightly greater, slightly less than the length needed. So there is a problem. Okay, the crocodile clip length isn't accurate. Okay, isn't accurate enough. Okay, you place it a couple of millimeters above or below the intended length. And now we have the plan experiment question. A student investigates the motion of a ball through air. Plan experiment which will enable him to investigate how the range of the ball, okay, depends on the angle at which it is launched. The angle, when you change the angle, we want to determine how the range of this ball depends on the. So the range, what is the range? Okay, what is the range? The range is the horizontal distance that the ball travels after leaving the end of the channel shown in figure 4.1. So you have the ball, okay, the ball will be placed at this point. It will start to roll down this flexible channel, and then when it leaves this point, we need to measure the distance, the range, okay, the distance, for example, from the ball as it hits the ground, okay, we need to measure this distance. This distance would be called the range. This is the range, the horizontal distance traveled by the ball, right? Right before hitting the ground. So we need to measure this distance, right? So the apparatus available includes a flexible channel and a selection of balls. In your plan, you should list any additional apparatuses, key variables, the steps, the table, as we are used to. First of all, the range of values, the independent variable. What is the independent variable? The range of values is what is the angle, right? The angle of this section of the, what's it called? Of this flexible channel, right? Of the channel. We need to give him a set, okay, a such as 20 degrees, maybe 30 degrees, 40, 50, and maybe 60 degrees, right? If you want to add 5 degrees, yes, 20, 25, 30, 35, yeah, it would be acceptable as well. So the range of values. What about the controlled variables? Controlled variables. So I have several controlled variables in this question. First of all, you can say the mass of the ball, right? Mass of the ball. The material of the ball. Hmm, Material. There is one really important, um, one really important controlled variable, which is the distance between this channel and the floor. Okay, this vertical distance between the channel and the floor, okay, has to be constant. It's a must. It must be constant. You cannot, okay, put it any further up or lower it down. The distance has to be constant. So the distance between the channel and the floor is constant. Okay, distance between the channel and the floor. You can also say the position from which the ball is released. Position from which the ball is released, right? We have several controlled variables. What about the apparatuses needed? Okay, the apparatus needed. He hasn't given us any apparatuses. We need two very important apparatuses, which are the ruler and the protractor, to measure the distance and to measure the angle. These are the important apparatuses. Okay, so we have the apparatuses, we have the key variables. Now, can I write down a simple explanation or some of the steps? What are the steps taken? Release the ball, release the ball from rest. Do not push the ball, release the ball from rest. Measure the distance or measure the range traveled in air by the ball, and then repeat and take average. Repeat and take. Don't have that many steps for this question. It's a very simple question. Not that many steps. Just set the ball, release the ball. Do not push the ball. Do not push the ball. Hmm. Now, can I draw a table? Yes, I can draw the table. Then you need only two columns in this table. Only two columns in this table, which are the angle, the independent variable, the angle in degrees, and the distance in centimeters. Angle in degrees and the distance in centimeters. Okay, as for the conclusion, what should I write down in the conclusion? Conclusion. For each independent variable, which is the angle, for each angle, repeat the experiment. Okay, repeat the experiment and take average. Record the results in the table. Record the in the table. And then when you record the results in the table, compare the results. You have to compare. How can I compare? Compare the results using a graph or by plotting a graph of the angle. Okay. Angle versus the range or the distance traveled. So instead of writing down the distance in the table, you can write down the range. It's the same thing. Okay, the range or the distance traveled.